These are your 6-5B notes, radical expressions. We're going to simplify some more, a little bit more complicated or just some complex problems. We're going to involve multiplying these things, foiling, distributing, adding, and subtracting. So to multiply radicals that have rational numbers with them, so if you look at number 1, there's a 3 and a 4 on the outside, and then there's the radicals 2 and 10. You can only multiply common roots. So a square root with another square root, a cube root with another cube root. You can't multiply a square root and a cube root. And so all you do is you simply just put the like things together. So rational number times rational number and irrational with irrational. So I just want to point out that the 3 out in front here is being multiplied by the square root of 2 times 4 times square root of 10. So it's one great big multiplication problem of 4 numbers. 2 of the numbers are nice and 2 of the numbers are not so nice. So if you want to write it down, you could actually write that down and put the nice numbers out in front and the not so nice numbers in the back. Or you can just do that in your head. You can combine the like things. So 3 times 4 is 12. 2 times 10 is 20. Now that we have it combined, we just got to clean that up. So 20 becomes root 4, root 5. Root 4 becomes 2. 12 times 2 is 24. So we end up with 24 root 5. So I can't forget the idea of taking out a perfect in that radical. For number 2 here, we're going to distribute 4 root 3 all the way through that problem. So there's a real number out in front of the square root of 27. It's just a 1. So you're going to do 4 times 1, which is 4, and 3 times 27, which is 81. Then we're going to take that same radical and apply it to the second part. 4 times 4 is a positive 16. 3 times 3 is the square root of 9. Make sure you write them down, okay? I know the square root of 81 is perfect. I know the square root of 9 is perfect. But when you start to simplify and multiply, you're making it harder on your brain. Write it down. Let your brain finish the distribution. Then the next line, your brain can concentrate on simplifying. So we know that the square root of 81 is perfect of 9. So now instead of 4 times the square root of 81, we have 4 times 9, which is 36. And then the square root of 9 is really 3. So when we had 16 times the square root of 9, now we have 16 times 3, which is 48. So when you add 36 and 48 together, we end up getting a nice rational 84. So that whole disaster up there of irrational numbers being multiplied and added together turns out to be a beautiful rational number. Okay, so that's multiplication. Now that you know how to multiply these things, now we can actually complicate our denominators a little bit more. So in the previous lesson, your denominators all worked out to be nice and perfect. Well, in this lesson, there's going to be an ugly radical in the denominator that we have to get rid of. So the process for eliminating the radical in the denominator is called rationalizing the denominator. If you listen to that word, rationalizing, it means you're making the denominator a rational number. If there's a radical in the denominator, it's irrational, and it's not allowed. So if you look at the first problem, the 5 over 2 times square root of 3, we have no problem with 2 in the denominator. Our issue is with the square root of 3. And so we need to make that square root of 3 turn into a perfect square. I know a perfect square that 3 goes into is the square root of 9. So to make the square root of 3 turn into the square root of 9, I'm going to multiply it by square root of 3. Whatever I do to the bottom, to be consistent, I also have to do to the top. So this becomes 5 root 3 over 2 root 9. Root 9 is perfect. That's why I picked to multiply by the square root of 3. Square root of 9 turns into 3, and then 2 times 3 makes 6. So my final answer here is 5 root 3 over 6. So what you see in that whole process, we created we got rid of the radical in the denominator. Okay, same thing for number 4, but before I start number 4, we have a fraction. So let's get rid of the fraction first, like we did yesterday. Square root of 4 over the square root of AB squared. Okay, the square root of 4 cleans up to 2. And this radical here, the b squared is perfect. So actually, I can take the b on the outside, and I'm left with the square root of a. So it makes sense to clean up your denominators and simplify your denominators before you try to rationalize them. So instead of trying to get rid of this whole mess, the only thing that we have an issue with is the square root of a. To make a variable a perfect square, I have one a, I need another a. So if I multiply both top and bottom by another square root of a, I'll get 2 root a over b times the square root of a squared. The whole idea, a times a is a squared is perfect, so the squared and the square root cancel, and so now what I have is 2 root a over ab. I just put the a out in front. So to be simplified, you can have the irrational value in the numerator, it just has to get out of the denominator. So that's a process called rationalizing the denominator. It helps us clean up the denominator, and we have to use multiplication to do so. Now we're going to talk about adding and subtracting these things. So in order to add or subtract radicals, they have to be like radicals. They represent an ugly decimal. So if you're going to put them together, you can only group them by the same ugly decimal. So in order to be the same ugly decimal, they have to have the same index. They have to be like a square root with another square root, or a cube root with another cube root. And then they also have to have the same number underneath. So you can only add like radicals. So an example of a like radical is the square root of 3b and 4 square root of 3b's. So it's just you have them in different piles. I have 1 square root of 3b out in front. I have 4 in the back. If I were to simplify that, that would become 5 square root of 3b's. You're just telling me how many of those ugly 3b's do we have. So they're both square roots, and they are both the same radicand 3b. So an example that they're not alike, okay, if I had the 3b and the 3b, but one is squared and one is cubed. So here it was a square root, here is a cube root. They're kind of small, but you can see that just because the radicands are the same, we cannot add those because the square root of 3b is a different decimal than the cube root of 3b. And then the last concept, okay, I've got a 2b and a 3b. They're both square roots, but they're different amounts. When you take the square root of 2, you get a decimal. And when you take the square root of 3, you get a different ugly decimal. So you can't put them together. You're telling me how many total ugly decimals you have. Okay, and all you do is you add or subtract the number out in front. I like to sort of relate this to variables. If I have an x and I'm adding 2 more x's to it, I can do that. I'm putting them together and I'm calling them 3 x's. If one of those x's was squared, we can't put them together. If one of those x's was a y, we can't put them together. So only like things, they have to be exactly like. So if you look at example 5, the way it's written, we wouldn't be able to add. But I notice there's a perfect living inside 8, and there's a perfect living inside 50. So if we simplify, we might be able to add these together. So I'm going to break down 8 into root 4 root 2. I'll come back to it, plus 3 root 25 root 2. So I broke them into perfects. Okay, the square root of 4 becomes 2. 4 and 2 make 8. So I have 8 root 2 for my first number. And then 25 becomes a 5. 3 and 5 make 15. So I have 15 root 2. So what we're looking at here is I have a pile of 8 square root of 2 ugly decimals here. I have 15 more of the same ugly decimal here. So I have 23 square root of 2 ugly decimals. Doesn't change into a different ugly decimal. I'm just telling you how many of those ugly decimals I have in total. That's what happens when you add or subtract. You add or subtract the outside numbers. Let's look at number 6. So number 6, 45, 80, and 20 all can be broken down into a perfect and a non-perfect. So I'm going to go right down the line and do that first. So 45 becomes 9 and 5, perfect and non-perfect. Minus 5, 16 and 5. 16 times 5 makes 80, plus 4, root 4, root 5. Okay, now you can see a common root there is 5, but we got to clean it up. So in this first pile of 3 squared root of 45, it ends up being 9 root 5. And in the second quantity, the square root of 16 becomes 4, negative 5, and 4 makes negative 20, root 5. I want to mention how nice and neat and systematic I am about this. I go through and I do my rewrite. I come back through, I circle, I cross off, I physically change this by crossing off the perfect, rewriting it as 2, circling 4 and 2. It allows my brain time to process, and I'm not trying to do a bunch of mental math. I can see the numbers that I'm multiplying. Okay, take the time to write it down, and then your brain can concentrate on the mathematics. 9 minus 20 is negative 11, plus 8 is negative 3 root 5. So negative 3 root 5s. I had 9 root 5s here, I had a negative 20 root 5s here, and I had 8 here. In total, I have negative 3 ugly decimal root 5s. Okay, last concept. We've already talked about conjugates before. I introduced the concept of conjugates when we learned about imaginary numbers. A conjugate is when you change the middle sign. So they're not opposites, they're conjugates. So if you have a conjugate, that's how you get rid of a binomial denominator. So this should be very familiar because of when we did imaginary numbers. So if you look at number 7, I need to get rid of that square root of 2 in the denominator. If I try to just multiply by a square root of 2, it'll take care of the first number, but then it moves it with the 3 because you got to distribute. So that won't work. So when you have a binomial in the denominator, we need to multiply by its conjugate, square root of 2 minus 3. Whatever you do to the bottom, we also have to do to the top. And so I'm going to distribute 5. So there's a 1 out in front. So 5 root 2. And then 5 times negative 3 is negative 15. In the denominator, the reason we pick conjugates is when we FOIL conjugates, the outer and inner terms go away. So I don't need to see them. They're going to be a disaster. They're going to be the ugly radicals. They disappear, so don't bother writing them down. So square root of 2 times the square root of 2 makes square root of 4. Outer, negative 3 root 2, and inner, positive 3 root 2, go away. Don't worry about those. Last is a positive 3 and a negative 3 makes negative 9. So now we just got to clean up. The top stays just 5 root 2 minus 15. You can't put those together because 15 doesn't have any root 2's. And then in the bottom, I've got the square root of 4 becomes 2. So 2 minus 9 is negative 7. The only thing I would fix here, and it's just a technicality, the simplification rules, they like a clean denominator. So that even means negatives. They really don't like us leaving a negative in the denominator. So you just change the sign of everybody. So the 5 square root of 2 becomes negative, the 15 becomes positive, and the 7 becomes positive. And there's your simplified fraction. Okay, one more time. So in number 8, the conjugate of square root of 3 minus the square root of 2 is the square root of 3 plus the square root of 2. So I'm going to distribute my 6 through. Okay, that's a rational number, so it just goes on the outside. 6 root 3 plus 6 root 2. And then FOIL the denominator. Square root of 3 times the square root of 3 becomes square root of 9. Write it down. Outer and inner cancel. My last terms, negative square root of 4. So I really can't do anything to the top. I can't combine those because one's a square root of 3 and one's a square root of 2. Those are different decimals. So I'm going to leave it as 6 root 3 plus 6 root 2 over 3 minus 2, which is 1. So actually, I wouldn't even write the denominator. And there you have it. So as a lesson summary, I just want to know what you would need to multiply the numerator and denominator by to rationalize the denominator in the following problem. That's a cube root. It's going to be a little bit more difficult. Give a guess. We'll see where you're at. You want to make the denominator a perfect cube. And I'm having a hard time finding my practice. There it is. Simplify that problem. So get them all to be common radicals and then add and subtract. Good luck.